Hi everyone. Good morning. Hope you can all see me down here. I'm not going to stand up there because I need to use this thing occasionally. I'm really excited to do this keynote. I'm going to talk to you about machine learning today. And so the first time I saw any kind of machine learning, computer intelligence kind of stuff, I remember it. I was at university. No, I wasn't at university. I was in high school in about grade 11. And I was going and visiting universities to see what courses they had to find out what I might want to do when I finished. And I went into the computer science department and spoke to a guy who was doing his fourth year thesis. And he showed me an example of what he was doing. And on the screen were a bunch of like randomly spaced dots. And he pressed a button and they slowly kind of moved themselves into a nice evenly spaced circle. And he explained to me that he wasn't telling those dots where to go. He wasn't programming a path for them. What he was doing was giving them some really basic instructions about try to be as far apart from other dots as you can and as far apart from the center as you can. And they were moving themselves. And he explained that this was the computer thinking for itself. This was artificial intelligence. And I remember looking at that demo and thinking, wow, that is not very cool at all. Like that. I was expecting Skynet stuff and he's showing me dots moving across the screen. Like, that's not interesting at all. So I kind of forgot about it. Ironically, the first time I actually got a little bit excited about what machine learning could do was when I was at the same university doing my fourth year thesis. A friend of mine was doing his thesis and he had built a neural network, basically a machine learned predictive model that he'd trained on a whole lot of like rugby league information. So he was basically setting up this machine learning model that could predict who was going to win a particular game. The cool part was he entered this is as part of his thesis, he entered this in a footy tipping competition, which is a competition for money where you pick who's going to win each week. And at the end of the season, the person who gets the most correct answers wins the money. He entered it in this footy tipping competition and he wipes the floor with everybody. So his predictive model won this money, and so of course I was interested in this. So I spoke to him and just said, so how easy is it to actually do this stuff? And he said, Damien, it is really easy. All you need to do is collect your data and like tune it and stuff, a bit of that kind of thing. And then just build up a deep neural network and make sure that you're using things like activation functions. You could probably use, a regressive analysis. By the way, how's your multi-dimensional calculus? So like any good computer science student, I abandoned that completely and I started writing Visual Basic for the government, which is true. So fast forward a few years and I've had a few different jobs. I now work for a small company called Microsoft. That's how you can contact me about any of the stuff I'm talking about now. I usually talk about DevOps though, and I'm not really going to do that today. One of the big advantages of working for a company like Microsoft, especially as a cloud developer advocate, is I get to work with incredibly smart people in a whole lot of different fields. So one of them, Seth Juarez, who if you watch Channel 9, which is Microsoft's kind of video channel, you might have seen Seth. I spoke to him about artificial intelligence and machine learning, thinking maybe he can give me some pointers. So you may not know this, but Seth actually has a degree in computer science with a minor in mathematics and a master's in computer science focusing on artificial intelligence and machine learning. So like, if you look at the difference between the two of us in a scale of how much we know about machine learning, I'm like starting to get the idea of it and he's like way up. He knows his stuff, right? So I say that as both a warning and as a promise that I'm coming at this from a programmer, a person who's been programming traditionally for many years, not as somebody who has a maths degree. And that'll probably become quite apparent when we get to the maths section. So where do we start? All right, so number one, what is artificial intelligence, machine learning, and deep learning, you may have heard as well, and even neural networks and stuff. This is all kind of a blur a little bit. Basically, artificial intelligence is this whole field of computers thinking like humans kind of think, or maybe better in some cases. Machine learning is how you do that, or one of the ways that you can implement artificial intelligence. Deep learning is a subset of that, where you just have more complicated machine learning algorithms and things. You don't really need to worry about this too much. The best explanation I've heard for the difference between artificial intelligence and machine learning is artificial intelligence is what you sell your customer and machine learning is what you're actually doing, right? So think of it like that. The difference is, so traditional programming, this is weird that PowerPoint is missing like individual letters and stuff. So traditional programming, as a programmer, you would provide an algorithm, you input some data, those two things work together and you get some answer out the back. Machine learning is a little bit different in that you don't really know what the algorithm is and you're asking the computer to determine that algorithm for you. So you're providing a bunch of correct answers and the data and saying, have a look at this and tell me what an algorithm is for determining these correct answers. Does that make sense? We're kind of flipping that around a little bit. Of course, once you have this algorithm that has noticed patterns in the data and can say, well, if you give me all of this stuff, then this is the correct answer, or what I think is the correct answer. You can take that algorithm and feed it back into what you would have done before. Add it to your application, and then when you give it new data, it can give you a prediction out the other end. Now, it's important to note that this is a prediction, because it's just noticing patterns. It's just saying, based on the data you've given me, I think this is the correct answer. It's not a correct answer necessarily. It depends on how accurate your model is. The other really important thing here, right on the left, that data, if you give it bad data, it's going to give you a bad model. And this is a big field now that's growing, which is ethics in data science and ethics in machine learning. If you give your machine learning algorithm a whole bunch of racist data to train on, guess what? You're going to get a racist model, right? And in some cases, racism and bias and things like that are so embedded in the stuff that we are getting the data from. Like if you look at crime statistics and things like that, there might be some in-place racism that you have to actively try to get rid of if you're going to train this model correctly. So something to think about. Bad data in will give you a bad model, and that'll continue these bad predictions. So that's great. What's interesting is that when managers especially hear about machine learning and artificial intelligence, they'll think things like, well, that's great, we've got a ton of data. Why don't we just get all of that data and then we put some machine learning into the data and then it can tell us stuff, like how we make more money. And it doesn't really work like that. To do machine learning properly, the first thing you need is what we call a sharp question. Right? So a sharp question is something very specific that you want answered. And there's really only about 5 sharp questions that make sense in machine learning. There is how much or how many, which is called regression. What class does this belong to, or classification? Are there different groups in this data that I've given you, which is clustering? Is this weird, anomaly detection? You might have seen that with banks and things like that, sending you messages saying, hey, this transaction that just happened doesn't look like your normal pattern. And then the last one's a little bit contentious. A few different people have a different 5th one, but I like this recommendation of what you should choose. Now, when you're training these, some of these need supervised learning and some of them are unsupervised. Supervised just means you're giving it all the correct answers, right? And then it's working out the algorithm. Unsupervised means you're giving it the data, but also telling it how you want it to look at that data, but you're not giving it correct answers. Today, I'm going to focus on classification, which is one of the ones that you use very regularly if you're doing machine learning and adding it to applications. So let's look at an example. So this is a canonical kind of out of the textbook example. This is, imagine you're a tennis umpire and you work casually for a tennis club and you want to know ahead of time, are you likely to be called in on the weekend? So you've collected all of this data, whether people are playing that day or not playing, and then what the weather report was. So you can see on the first one, people played, the outlook was sunny, the temperature was low, and it was quite windy. So you've got all of this data, right? And you want to create this model to tell you, based on the outlook temperature and whether it's windy, are people likely to play or not? Now, the programmers amongst you have probably looked at this data and already tried to work out some kind of pattern to this, and you might have ended up with something that looks a bit like this. It's basically a decision tree. So you're saying, well, when it's overcast, they always play. When it's sunny, it depends on the temperature and so on. So this is basically what you're going to get as an output from your machine learned model. Ideally, you would get something like this because it's quite concise and it's generalized. So So when you actually run through this model, if you add it to your application, you can follow that path down, and then obviously you predict that they're going to play with that last one. So that's great. And it seems quite straightforward, but there's a couple of things I want to point out. Number one is that the data that we can see here is quite nice. Like, it's very consistent. There's nice values in there. But really, you're going to get terrible data, right? You get, like, the data that you get for any of this training is never pretty. What I would say is, if you're doing machine learning stuff, the data science part and the data filtering and exploration and things like that, that's going to take the vast majority of your time. Right? There'll be missing data, there'll be incorrect data, there'll be duplicates, there'll be fields that you probably think make sense, but then when you run models, it doesn't make sense at all. There'll be outliers, things that are completely against the trend, and all of this stuff is really important for getting a good model out the other end. So you're going to spend a lot of your time tweaking this data to make it look really good. So there's one thing. The other thing is, you can see the graph we've got there has 5 leaf nodes, like 5 endpoints, and the grid has 8 different rows. That means that our graph is quite generalized. And generalization is kind of a hard problem with machine learning. It would be easy to draw a graph that had 8 end nodes, right? And it just directly maps the information that's in that table. If you start doing that, and remember, we're not going to be talking about 8 records, we're going to be talking about thousands and thousands. But you could easily get a graph that directly represents the data that you've given it, and that's a problem we call overfitting, which means that your predictive model is really, really good at predicting your training data and terrible at predicting the real world. So there's a technique we use in machine learning which is pretty basic. We basically take all of the correct answers that we're going to feed it and we split it. You can generally use anything between 50 and 90%, but you use a lot of it for training data, and then you use some of it for test data. So you train it on, the 80%, and then you run it by the 20% to see how accurately it calculated those answers. And the idea is to get this nice balance between them. So this is how you go ahead with that stuff. So we've looked at a really basic example of a grid with a few different fields. What about a slightly harder problem? Like, we could solve that problem as programmers by ourselves. But a slightly harder problem, like maybe reading a handwritten number. How would you write an algorithm yourself to tell you what number is in a box that somebody has handwritten? You can see how that's a much fuzzier question, right? You can't just pick a pixel and say, well, that's a 2 because there's a pixel in this spot. It doesn't work like that. What we really want our machine learning predictive model to do is give us basically a function. If I give you a picture, I want you to look at that picture and give me a digit back. So that's what we're looking at. So we're really trying to define a function. So we call this, we'll call this h. H is our function, and x is what we give it, our picture. So h is what we're trying to find, what we're getting our machine learning model to find, and x is what we give it. But what do these really represent when we're giving them to a computer? Because you can't just say, here's a picture. Computers deal with numbers. And to do this stuff, there's a lot of maths behind it. So you need to really represent this stuff in a way that can be mathematically operated on. So we'll walk through that. To find an h, the aim of finding an h really needs 2 things. We need a way to mathematically represent these examples we give it. So we need to turn that picture into something that can be mathematically operated on. And then we need a function that can separate those different classes, so what the different numbers are. So let's simplify this a little bit just for demonstration purposes and say, rather than trying to find a number, which has like a 28 by 28 pixel field, let's do a 3 by 3 set of pixels. And let's decide we want to determine whether the top is darker than the bottom, right? Fairly straightforward. And again, we could probably work this out ourselves. There's probably a way of doing it ourselves, but we'll say the machine learning model is going to do this for us. So the first thing we need to do is represent this mathematically so it can be operated on. So this is what I've come up with. So we have our class, which is 1 or 0, depending on whether the top is darker or the bottom is darker. So that first row is representative of this number. And then we have a level of darkness. It's kind of the opposite of your hex code if you're familiar with design. So you can kind of see how we might work this out already, but this is a mathematical representation of what we have. So we have our class with our labels, and our labels are 1 and 0. And we have our features, is what we call all of our inputs. And we have 9 features. So we have that. What we want to do is we want to take all of these inputs, all of these pictures that we've got and the representations, and we'll call those inputs X. So we've got 9 X's in our case, the 9 pixels, and how dark they are. We want to do something to them, add them all together at the end, and come up with an answer that will tell us whether it's darker at the top or the bottom. So one way we could do this, just to demonstrate what stuff might happen, is you might look at it and say, well, if we multiply the top 3 or the first 3 digits by 1 and the last 3 digits by -1 and then add them all together at the end, we'll end up with a number that's either above 0 or below 0. If it's above 0, it's going to be dark at the top. If it's below 0, it'll be dark at the bottom. So this set of zeros there, or set of circles there, that represents something we're multiplying it by. Right? So I'm going to call them W, because that's what we tend to do. So here's another way of writing exactly the same thing that's a bit more mathsy. We have a vector, or think of it like an array, of X's. So these are all our numbers, our inputs, how dark each of those pixels are. We have a bunch of W's, and in our case, the first 3 are 1, and the last 3 are -1, in the middle, 0. And then we multiply them together, and in maths, that's a dot product. We're multiplying 2 vectors together, and we end up with another vector, which is all of the multiplied values. We add them together, we get a number that's less than 0 or above 0. Kind of make sense? So this is maths, right? And this is another way of writing it. And this is our function. This is H. This is W transposed with X, so these 2 vectors multiplied together. And we also do a plus B. If you remember like your basic maths from high school, you might recognize this as like the AX plus B, which is the definition of a straight line. Right? The difference is a straight line is 2 dimensions. This is 9 dimensions. Still works though. The math still works. So this is what we're working with. And this is what we call our model function. This is what we are saying, right, this is how we define how to separate our 2 classes. We just need the computer model to tell me what W's are and what the B's are. With me so far? There's not too much maths yet.
Is there an array of B's or not?
At the moment, there's only 1 B. So the question was, is there an array of B's? So at the moment, there's only 1 B, but hold that thought. So what we're really doing is doing a decision boundary. We've got all of these different inputs, and we're trying to draw this boundary that separates the 2 classes, and that boundary is defined by a function. So you can think of it like this. If we had 2 inputs, you could map them to a 2-dimensional graph, right? And all of the ones up this corner are heavy at the top, and all the ones at this corner are heavy at the bottom. So you can draw this line. So this is a linear function. We call this function basically a linear regression. So we're basically drawing a line across the thing. So this is in 2 dimensions, is a line. Actually, if you're in 1 dimension, you only have 1 feature, then it's a point. If it's above a certain number, then it's in one group. If it's below a certain number, it's in another group. 2 dimensions, it's a line. 3 dimensions, it's a plane. 4 dimensions, it's a hyperplane. And then I assume they just got sick of naming it, so it's hyperplane after that. So in 9 dimensions, it's a hyperplane, right? So this is our function. We're going to work with that. We just need the computer to work out what W and B is, or what the array of W's are and what the B is. So let's go back to our complicated example here. Can we use that to solve this problem? So let's try it, all right? So let's first represent this mathematically the same way as we did before, keeping in mind that this is now 28 by 28. So there's 784 different features now. So we're talking 784 dimensional space. Complicated, but it's still fairly straightforward. We've just got 784 different inputs. So this is an example of a 0 that somebody's drawn, right? So let's take a whole bunch of these, plus the correct answers, and provide them as our feature, as our set of features and our set of input data that we want to train on. So we can see on the right there's all of our features. We've got 784 in each row. And then on the left, we've actually got more than 1 answer. We've got 10 labels. What we're actually doing is saying, what's the probability that what you drew is a 0? What's the probability that it's a 1? What's the probability that it's a 2? So we've got more than 1 function that we need to work out. This is a technique called one-hot encoding. which basically means each one of these things is separated. And we can see with this test data, we can say there's a 100% probability that the first one is a 8, 9, 7, something. I don't know. I can't remember how I encoded it. So we've fed in all this correct answers, right? And we're going to train it on that. But in our example, we only had one sum at the end. So how do you actually get more than one of these for these different labels, these different probabilities? And the answer is you just do this multiple times, right? So you have a set of W's and a B for your 0. You have a set of W's and a B for your 1, and so on through all the numbers. Now the X's stay the same, so we don't need a different set of X's for each of them. The input's always the same. So this formula that we had, this formula still works. It's just that instead of W being one vector, one array of numbers, now it's multiple arrays of numbers. And there's a way of representing that, and it's called a matrix. So we have exactly the same formula. It's just that W is now a matrix, and B is now a set of B's. We now have an array of B's. But it's the same thing. It's a dot product. So that W array there is going to be 784 values high and 10 wide, because we have 10 different values of W. And our B's are going to be 10, I think. So we basically have this long thing, and we end up with an array of answers, an array of Y's, which is going to be ideally our correct answer. All right, still with me? It gets a bit mathsy, doesn't it? But hopefully we're still going. Right, so here's our formula. This is what we're going to say, right, I need you to work this stuff out for me. But we still haven't answered this core question. What is W? Like, how do we get W? We're giving it a whole bunch of data and saying, find W for me. How does the computer do that? Well, it turns out the answer's pretty boring and straightforward. You basically try some stuff, and then you see how wrong you were, and then you adjust it, and then you go back to see how wrong you were. And you just do this over and over and over again. Remember, we're splitting our data, so 80% of it is used for this training, and then 20% to test it at the end. You can iterate over that over and over and over again and slowly get to a point where the W's are good. So there's two things here. See how wrong we were. How do we do that? Well, with this linear regression, and with a lot of other things, here's a nice formula that you do not have to know, right? This is a squared error. It's basically a way of saying, given my function, so actually I'm going to explain this. So h of x is our function. This is our W transposed with x plus b. In fact, let's just do that. That's our function. So with our w's and our b's, let's just run that. Let's subtract them from the correct answer to find out how far off we are, and let's square it and get an average and things like that. So we're basically comparing the answers that our model gave us based on some W's with the correct answers, seeing how wrong we are. So the idea is to minimize this. We want this number to be as low as possible. So to simplify, let's just call that whole cost function, we'll call it J, all right? We don't need to worry about all that complicated stuff. So J basically represents, given some W's, how wrong are those W's? How far off the correct answers are we? So we want to minimize J. How do we do that? Well, if any of you did kind of calculus in high school and things like that, you might recognize minimum as something that gets used in calculus a lot. So if we think about, let's say our cost function, just to simplify, is x squared. You can see here's the graph of our cost function. We want to kind of get it to tune our numbers so our cost is as low as possible. Our cost is down to 0. We can see if our W's are too far to one side, then we get a big error. If they're too far to the other side, we get a big error. So we want to kind of slowly come down and get this cost as small as possible. The way you do that is you get the derivative, and that gives you in our case, it gives you a straight line. It basically lets you find that local minimum. Don't need to know this stuff. But the point is, this is a way of finding out how to get down to make that as low as possible. Now this is, again, one variable, x squared here. We're talking about 784. Great thing about calculus, and I can't believe I said those words. The great thing about calculus is it works regardless of how many dimensions you have, right? So all you need to do is say, get the derivative of this, and it'll tell you which direction we want to move our stuff. So in general, to tune our W, to optimize our W, we want our cost to be as low as possible. So we look at the previous W's we got, we subtract our derivative of the cost function multiplied by some kind of learning rate. So if we go back to our x, if we're at -3 and we say, oh, we need to adjust in this direction, we move 6 this way, now we're at +3, oh, we need to adjust, we'll move -6, and we'll just bounce back and forth. We'll never get to our minimum. So this learning rate is a nice way of slowly descending down this gradient. And that's called gradient descent. So this is a way of optimizing what we end up with. So let me summarize what we've got so far, because we've kind of reached the point where now we can do some training. Our x's are a representation of whatever data we want to give it. And in our case, this is a vector representing the darkness of all the pixels in our image, right? You could also have your x's as, a value for how the outlook is, whether it's sunny, overcast, a value for how windy it is, and so on. So this is just a mathematical representation of what you're giving it. Our y's are our answers. And if you have more than one class, one hot encoding is a nice way of doing that. We have our model function. So this is the thing that we're giving to our training program to say, I want you to work out the W's and the B's in this, but this is the algorithm that you're going to use. And this is linear regression in our case. We have our cost function or our loss function, and we're using that squared error to say this is how wrong we are. And then our optimization method, which is just called gradient descent. Cool? I'm going to take a drink because I just did a lot of talking. Any questions about this? No questions, and there was multi-dimensional calculus. That is a massive win. Can somebody write to my boss? All right. So this is what it looks like in TensorFlow. So this is exactly what we've just talked about. This is actually real stuff that's training. So this is TensorFlow here. In Python, we're using TensorFlow libraries. Here are our x's. We're basically just saying, here's a placeholder that is 784 wide, and we're going to give you these numbers as you do your training. Here are our y's. Here are our 10 one-hot encoded correct answers, and we're going to give you them as we go as well. Here is the model that we're using, and I'll come back to that. We're just saying this is a linear model. Here is our cost function, and it's the average of the difference between our hx and our y squared, and then we're reducing that mean. And here's our optimization function, which is just straight in the TensorFlow library. It's just gradient descent optimizer. And we're saying, here's my cost function, use gradient descent to optimize that. So this is pretty much exactly what we just talked about. TensorFlow makes it quite easy, and if you're using CNTK or something like that, there's similar libraries for that. The linear model, by the way, we've defined that ourselves. This kind of graph of all of the inputs going to all of these functions and then all the way out again is so common that we call it dense, or it's called dense. So we're just saying, here's your inputs and give me 10 outputs. So this is really basic. We're just saying to TensorFlow, here's the model I want you to use. So what does this actually look like? When we do our training, we want to keep track of how that training's going. So there's a tool called TensorBoard that will track our logs as we go through, and it will give us our accuracy. So we can see here that when we started training this, we got to about 82%-ish accuracy, 81%, 80% accuracy, but we didn't really get much better as we trained more. So we're trying to adjust and optimize these W's and the B's, but we're not really getting any better after a certain point. Now, is 80% good for recognizing a number handwritten in a box? Not really, no. It's not great. Like, you probably wouldn't want to use it in your application. So why is it that it's not great? Well, remember that we were talking about having this linear answer. So if you think about it, we're basically saying, I want you to find a line that nicely separates my data. But our data doesn't look like this with a drawn number. It might look more like this. There's no good straight line that's going to separate these two classes. You might get one that'll give you an 80% value, but that's not really good enough for practical purposes. So we need to make this a non-linear answer. So that linear regression that we did, the W transpose with X plus B, that's not a good enough model function for the learning model to be able to get a good answer. So we need to make it more complicated. What we could do is we could just stack multiple functions. So we've worked out an H, this first layer here, this one here, We've worked out that h. Why don't we just work out a different h and use those ones as inputs and then put multiple layers in? And these are called hidden layers. Hidden layers are ones that feed into other layers. So you basically don't see them unless they're on the very edges, and we call them hidden layers if they're inside. The problem with this, though, is if we use that same linear model function for each of them, we end up with a linear result anyway. You can think of it like if we multiply everything by 3 and then do another function that multiplies it by 5, you may as well have just had one function that multiplies it by 15. So we're just doing these linear models that are going to give us a linear result. So we need a non-linear answer. We need something that's going to give us a more complicated curve, a few different features like that. So we add in an activation function, is what it's called. Now, an activation function can kind of be anything that makes it non-linear, so makes it not a straight line or a plane or a hyperplane. Some really common ones, I really like this one. This is a sigmoid function. I like it because of A, the name, and B, it's a really kind of nice curve. You don't need to do anything this complicated. There's one that gets used probably more than any other in machine learning called ReLU was the short name for it, but it's called rectified linear. And it basically means I don't care about it until it hits a certain point and then give me the value. So it's almost like a switch to say if it's below this, don't care. If it's above this, great, give me that value. And that's enough to make it a non-linear answer. So we can change our TensorFlow to make this more complicated. So there's actually a few changes here, but the important one is here we're just doing this, this non-linear answer, and we've basically created a convolutional neural network, which you might have heard. That's all that this is. It's called a convolutional neural network. So we've got our cost function, which we've actually changed. This is a different cost function. This is one called softmax cross entropy with logits version 2. I have no idea what that means, right? But it's basically a cost function that will tell us how badly we've done. And we've actually changed our optimizer as well. So instead of gradient descent, we're using one called atom optimizer, which is similar, but it uses things like momentum and stuff, which is kind of cool. But again, I don't know what that means. So we've just changed the functions that are used to tell us how wrong we are and then how to optimize our numbers. Our convolutional neural network is a bit more complicated. And by the way, I'll give you the link to all of this code if you wanted to run it yourself. But when we do run this, we can see we get a lot more accurate, and we're still slowly getting more accurate as we go along. We're tuning all of these hidden layers, the values that we're giving it, and all of that kind of stuff. And we're ending up with 98, 99% accuracy here, which is quite cool, right? So what does this actually look like? I mean, this has all been very theoretical, and I've shown you screenshots of code. So let's actually do it. So here is a WPF application, which is using the predictive model we got. It's basically a function where you give it x's based on whatever I draw, and it gives you the correct answer. It's the h. So if I do something like I draw a 3, by the way, I'm doing this on a trackpad, so this is horrible, and press recognize, it'll use that model to predict what number I'm using. If we do 4, because I know it's quite bad at 4s, or I'm quite bad at 4s. Oh, it did it, great. Way to actually work when... Would you recognize that as a 4, everyone? There you go. So here's the problem, is it's still not 100% accurate, partly because my writing is really bad. But just to show you what's actually happening, I've put a handy breakpoint in the code. So let's enable that, and let's just do this again. So recognize, and let's hover over our P. And can you see this? This is a set of 10 different values. Maybe I will go down a bit. Can everyone see that? This is a set of 10 different values. We can see that a lot of them are really, really small with negative exponents. And then 8, it reckons it's 99.6% sure I drew an 8, right? So there's still a bit of work to do. It's actually got a tiny chance that it's a 9 as well, which is not great. 4 is higher than some of the others, but it's not high. So again, it's not 100% accurate, this stuff. But it's enough that we have a relatively okay predictive model. Cool. Now, all of this code, by the way, is available on GitHub. This was actually written by Seth Juarez, so it's good. That's just a shortcut to the GitHub repo. Have a look. He's got examples of all this stuff working. He just refactored it a few days ago as well, so it looks much, much nicer. By the way, I'll put all of the URLs I'm going to show you at the end if you wanted to save the memory on your camera. I ran out of memory on my camera, my phone, the other day. So anyway, is anybody there thinking, okay, that's cool, but there's no way that I could do this stuff to actually add AI or machine learning to my application? Like, how am I going to train this model? So that model, by the way, ran on my laptop in a VM, or the training ran inside a VM on my laptop, actually in Visual Studio, which is what you just saw. And it took about an hour or so to get that predictive model, right? You can, if you have a machine with a big GPU and things like that, then it might be faster. Azure also offers things like batch AI and so on, where you can send batches of processing up and it will do the training for you on gigantic machines. But do you really want to work all this stuff out yourself? Like, that's really complicated just to find something that can read some handwriting, right? Think about it like if somebody asked you to add PDF recognition, so display a PDF on the screen for your application. Would you go to the PDF spec and start sitting there writing code to read a PDF? No. Like, people have solved that problem. I'm just going to use that stuff, right? So Azure has a bunch of cognitive services, and AWS has a bunch of these as well, and Google Cloud Platform has a bunch as well. You should use the Azure ones because they pay my salary. But so there's a whole lot of cognitive services. There's a ton of these, and they offer things like handwriting recognition. So let's just show you what that is if you're actually doing it properly. Can somebody, actually I was going to ask you guys, can the 5 people in this row, can you just call out a digit and I'll write it down?
7.
Yep.
6.
6.
3.
3. 2. 1. All right, let's just get my Facebook shield off. And let's just do this. Take a screenshot. And this is just calling out to Azure via my mobile phone, which is in a gigantic cement box. So maybe this would take a little bit. Ooh, that wasn't good. Let me try that again. This is why, like, pun intended. Wow. Did you guys do that on purpose? Let's do that. All right. So I'm not giving it any instructions beyond just read what I've written down. Okay, it missed a one, but you can see it's a little bit better than what I have with my example. Well, when I did it again, it was a little bit better than what I had. So there's that, right? So you don't have to solve this problem yourself. There's a solution to this problem already. So I thought, what better opportunity than a DDD keynote to try and do the hardest demo that I could do. And so I bought a Raspberry Pi when I was on leave not very long ago, and I thought, why don't I do this stuff and actually get it to recognize stuff on a Raspberry Pi? Like, so that handwriting recognition, you don't really have much input into what kind of stuff it's going to recognize, but there's a bunch of cognitive services where you can. They're custom cognitive services. So all of those layers that you've seen, they might be good at doing things like recognizing the edges of an image. And then a bunch of those get fed into the next layer, and they're good at recognizing an eye in a person. And then they get fed into another layer, which is good at recognizing how far apart the eyes are and so on. So Azure can pre-train a lot of these layers, and then right at the end, you can just give it the objects that you care about, and the training takes a lot less time, and you end up with quite a good model. So I thought, let's use a Raspberry Pi to recognize a couple of objects, and just use the camera on that, call into Azure, and try and get it to identify different objects. This is one of my favorite cognitive services. Right? So I did. Let's just turn the camera on again. So I'm going to get it to recognize this. This was my favorite Matchbox car as a kid. I mean, it's a sparkly limo. Obviously, it's your favorite one. So there's that one, and then a little Lego figure. So I'm getting it to recognize those two. Now, ahead of time, because I know how this stuff usually goes, I took a whole bunch of photos, and I added them to cognitive services, and uploaded those images, and basically said, all of these pictures are of the Lego person. All of these, well, that's a horrible one for training, but anyway. In fact, the shadows on this make it really difficult. So, and all of these are of the car. So I've basically given it 22 pictures of a car and 22 pictures of Lego. This is just a pretty basic example, all right? So what I could do, once I've done that, I can click train. It'll take a few seconds and it'll give me a predictive model. And it'll tell me how accurate it thinks that predictive model is. Admittedly, I've only given it like 37 images. It's not going to be 39 images. It's not going to be magnificent, right? It reckons, though, that if a tag is predicted by the model, it's 100% likely to be right. But if there should be a tag predicted, it's 92-ish% confident that it's going to tell me that it's a car or a Lego person. So I could hit that URL just like I did with the handwriting recognition, and it would tell me, you know, here's the answer based on the images. But this is a little like electronic device here. I don't really want this thing to be calling the internet over and over again, right? So instead, I'm going to use another feature which lets me download that model and export it to a bunch of different formats, including a Docker file, which is quite cool. So you can basically, if you can run Docker on a thing, then you can run a predictive model on it as well. I'm going to use TensorFlow, which is aimed at Androids. And by the way, quick shout out to Michael Ridland, who is doing a talk, I think, later on in the day where he does a lot of this stuff and actually gets it running on mobile phones and things like that. I'm going to run it on the Raspberry Pi. So let's download that TensorFlow export. I'm going to put it in my downloads folder. And I'm going to switch to one of my other 1,000 desktops. There we go. And we just got that zip. And let's open that up. And let's grab these models, and we'll copy them over the top of the models that I already have. Just so you can see I'm doing this, replace them. Great. Now let's go to our code. And this is our computer vision model. So I've got a little Python script which lets me take the photos, and I've got another one which uses those photos to predict, uses those photos, runs them through the model that I just copied in there, and predicts what I've actually taken a photo of, right? And you can see that I've modified the labels and the model itself. So I just downloaded this model, I've added it to my source. So I'm going to just commit this. Let's just add these, and then we will commit and push, and hopefully it doesn't complain that I'm on a weird network. So let's push that out. And so this is basically just pushing it back up to GitHub, and I'll give you the link to the GitHub repo as well. There we go, that's succeeded. So for those of you who are wondering why I'm not talking about DevOps this time, I just shoved a bit in. So I'm actually using Visual Studio Team Services to deploy this to the Raspberry Pi. There's a VSTS agent, well, a deployment agent that's running on the Raspberry Pi. There's a blog post that I've written about how to actually do that, because there is no build for that agent that will run on a Raspberry Pi. But the advantage of this is hopefully, if everything's okay, and I don't accidentally disconnect this, we should be able to see, I'm just going to hold this up while I take questions. We should be able to see when that's deploying, it'll go yellow, and then it should go green if it actually succeeds. But while we're waiting for that, oh, there we go, that's yellow, by the way. And then green. So this deployed to the Pi. I could actually run an agent on 100 Pis if I wanted to, and it would deploy them on all of them. Now, should you do this? No, you probably shouldn't actually. I just did it because it was fun. But there's another tool called IoT Hub that Azure has, which does this a little bit better, right? You can deploy it to 1 million devices, and it'll track what's on those devices and things like that. All right, so that's been committed. It's actually been updated. Where's my Raspberry Pi? It's dropped off. Let's just reconnect. So I'm just VNCing into the Raspberry Pi just to make everything really complicated. And you can see here was the versions. Is that big enough for everybody? Yep, good. Here are the versions. I've got version 17 and 18. Now I have version 20 as well. I must have deleted 19. Or a build failed or something like that. So let's go to 20. Let's go to Azure Custom Vision, and let's say go. And now we should get on our screen what this camera sees. And we can test out our predictive model to find out what it's actually doing. All right, we've got a little wait symbol. Great. Oh, this is going to be slow. But anyway, so let's do one with the car. All right, let me just press the button. And let's have a look at that display, and it reckons that that's a car. All right. Let's do a little Lego person. Lego. So kind of cool. You can also see it was super confident in those, right? It was 100% confident, this is to 2 decimal places, that it was a car in that case, and 100% confident it was Lego. Now, if I trained it more, I could probably get it to recognize when both of them are in the image, and so on. I could basically improve this model if I gave it a bit more information. I could give it a bunch of pictures of different Lego cars, and then give it a brand new Lego car, and it says, well, based on what I know about Matchbox cars, this is going to be a Matchbox car, right? The other cool thing about that is that's working totally offline. Where did my slides go? That's working totally offline. So if you're thinking that this is actually a little bit expensive maybe to use these services rather than your own, that's offline, so that's free dollars, $0, right? By the way, the links, the Demo Pi link is the one to the GitHub repository that has my code in it, and that Pi agent one is a blog post I published last night about how to run an agent on the Raspberry Pi. If you're wondering about how expensive this is, 1,000 of those calls, if you actually go back to Azure, cost you about $1 US a month. That's up to 10 a second as well, which I don't think this thing is capable of doing 10 photos a second, so we're good. It depends basically what service you're using, but anywhere between $1 and $3. So, enough of that. If you want to see a bit more detail about that, I'll probably hang out at the Microsoft booth and carry all this stuff with me a bit later if you want to see a bit more detail. But going back to the machine learning stuff, this is what we talked about. You start with a sharp question, you give it a bunch of data. In this case, we just took some photos, that was our data. You train it by giving it a model that it cares about. That model comes out at the other end, hopefully makes good predictions, which hopefully makes you money. And this is really how that machine learning process works. Or you can just put cognitive services in and skip all of that stuff anyway. Right. So there are the links. If you want to take a photo, this is the one to take a photo of, but I think you've already done that beforehand. I would strongly encourage you just to have a look at some of this stuff. The $1 a month stuff is great, but there's also ones that are $0 a month. So everything I showed you is 100% free. I didn't use anything that uses any more than anything that needed me to pay any money, right? So just give it a try. It's quite fun to work this stuff out. All right, and that is all I have time for. So thank you very much for your time, and I hope you have a good day.